Sometimes we have a function that's not one-to-one, but we really want to pretend that it has an inverse. So this is a very common move in math, actually. Something unpleasant happened. We want to pretend that what happened is actually nicer. So we're going to do something to whatever object we're working with to make it act like it's nicer. In this case, if we have a function that's not one-to-one, but we want to have something like an inverse for it, what we're going to do is to restrict the domain of the function to a slice where it's one-to-one. So let's suppose we have the function f of x equals x squared. Right? That's not one-to-one. So just like let's pick a positive number, right? F of 2 is 2 squared is 4. But also f of negative 2 is negative 2 squared is also 4. So the pairs 2, 4 and negative 2, 4 have the same output, have the same y coordinate, namely 4. This function is not one-to-one. So what can we do about it? Well, let's consider, in order to get those pairs, we had to pick a positive value of x and its opposite, which is a negative value of x. So if we restrict our domain to only positive numbers, well, do we get something one-to-one? Yeah, we do. This is one-to-one because the only pairs of numbers that have the same square are the pairs in the form some number and its opposite. Only one of those is ever positive. So if we restrict our x's to being positive numbers, well then, we're not going to have any two x's that correspond to the same y. And so we can actually take an inverse of g. G, with the restricted domain, is actually one-to-one. And furthermore, we know that 3 squared is 9. That is, the pair 3, 9 is in the relation G, which means that its reverse, 9, 3, is in the inverse. In other words, if we take input 9 to G inverse, we get output 3. G inverse of 9 is 3. Now, that's one restriction we could put on the domain of our f of x is x squared in order to get something one-to-one. We could also restrict the domain to contain only negative numbers and 0. So if h is the function x squared with the domain restricted to negative numbers and 0, well, that's going to be one-to-one for the same reason that our function g was one-to-one. That is, again, the only pairs of numbers where if we square them we get the same thing are a number and its opposite. Only one of those is going to be negative. And we can actually figure out this inverse with some trial and error. So for example, negative 3 squared is 9. Notice negative 3 now is in the domain of h. So the pair negative 3, 9 is going to be in the relation h. Switch the order. The pair 9, negative 3 is in h inverse. And so when we have the input 9 to h inverse, we get the output negative 3. So for G, we restrict the domain one way. Our inverse is a function that with input 9 gives output positive 3. With H, we restrict the domain in a different way. And our inverse then is a function that with input 9 gives output -3. And so those are different inverses, right? They do different things to 9. But that's okay because g and h are different functions from each other also. They're different functions because they have different domains. So they're not the same function because they have different domains. It turns out that this restrict the domain and pretend there's an inverse move is one that comes up all the time. What do I mean by that? Probably in every math class you take from now until you stop taking math classes, you will see this move at least once. This is very useful when we're solving equations. It's very useful when we're trying to create new functions.